This conference will now be recorded.
Well, hello everybody, and thanks for joining our GSA webinar call. Today, as you know, we're going to be going over advanced weather systems and the considerations for those systems for spaceports specifically. We have a real fun agenda, a presentation by Will Cromitty from Spire Global, and also another presentation from Bill Conway from Weather Decision Support Systems. I want to take just 1 second and welcome new members to GSA. Justine Ruff from Midland Air and Spaceport, and John Trishidi from Midland Development Corporation. So we're delighted to have you as members. Today's session is being sponsored by Weather Decision Support Systems, and our title sponsor is RS&H. You are currently muted by Steve. If you need to talk during the course of the presentation or presentations, please just unmute yourselves so that you'll be able to be heard. In the center top, you'll see a toolbar, view everyone. If you wish to see the speaker only, just tab down to the speaker only and you'll be able to see him or her. And the chat box is up in the top right in the circle. Well, with that said, I want to turn it over to our chairman, George Neild, for his report, and he will then introduce our speakers. George, turning it over to you.
Thanks, James, and greetings, everyone. It's good to have you all with us today. As I was preparing for our discussion today, I was looking back over the activities of the last few months since we had our big November event, and I am just astounded at all that is still going on in the commercial space community. Just to remind the group of some of the things that have been going on, Astra had a successful launch of their Rocket 3.2 on December 15th from the Pacific Spaceport Complex in Alaska. Blue Origin had the 14th launch of their New Shepard reusable launcher from West Texas on January 14th. January 17th, Virgin Orbit had its Launcher 1 deliver 10 payloads to orbit for NASA's Launch Services Program after taking off from Mojave Air and Spaceport under the wing of a 747 carrier aircraft. January 20th, Rocket Lab's Electron booster launched the communications satellite from New Zealand. January 24th, SpaceX delivered 143 satellites to orbit using its Falcon 9 rocket, and then landed the first stage on a drone ship, marking the 73rd time that they had recovered this stage. On January 26th, we heard that Axiom is going to fly a private crew to the International Space Station. They're scheduled to ride in a SpaceX Crew Dragon launched by a Falcon 9 sometime in early 2022, so about a year from now. And the mission will be commanded by Michael Lopez Alegria, former NASA astronaut, and will include a US entrepreneur, a Canadian investor, and an Israeli businessman. Then on February 1st, SpaceX announced that a mission that is called Inspiration 4 is going to become the first all-civilian space mission, and that'll be in the fourth quarter of this year, led by Jared Isaacman, founder of Ship for Payments, and 3 others. And then just a few days ago, it was announced that Haley Arsenault, who's a bone cancer survivor and is now a physician assistant at St. Jude Children's Research Hospital, is going to be one of those on the mission, and that will make her the youngest US citizen to fly to space. So pretty exciting there. SpaceX has also been conducting their flight test of their Starship prototypes at their site down in Boca Chica, Texas. They had a launch of SN8 on December 9th and SN9 on February 2nd. They had a static fire yesterday, and we may see the test flight of FN10 in the next few days. February is a big month for visiting Mars. On February 9th, the UAE and their HOPE spacecraft successfully entered Mars orbit. On the 10th, China's spacecraft entered Mars orbit. And of course, on the 18th, NASA's Perseverance rover landed on Mars. Very exciting. If you haven't had a chance to see those high quality video of the landing of the robot, please check it out. It is really awesome. Some very, very high-def pictures of the parachute deploy and then the touchdown. Very impressive stuff. February 20th, Northrop Grumman launched an Antares rocket carrying a Cygnus spacecraft to the ISS. So a lot of launches going on. On January the 8th, FAA and NASA signed a new memorandum of understanding to support commercial space activities. And as part of that agreement, the two agencies agreed that they would try to build a transparent framework for industry that avoids conflicting requirements and multiple sets of standards. And they will seek out commercial interests in a pilot program for a point-to-point suborbital test program, which we've been talking about for a while. And they'll also try to look for areas for collaborative research opportunities, including sharing of medical data to understand the effects of spaceflight on space vehicle occupants. In other news, January 15th, the FAA granted Space Florida a license to operate the Cape Canaveral Spaceport as a launch and re-entry site at the shuttle landing facility. So now can do both launches and re-entries there at Cape Canaveral. Previously, their license was only for launches. And then in the FAA Reauthorization Act of 2018, Congress had directed the GAO to conduct a study on potential mechanisms to provide federal support to spaceports and to provide recommendations on funding options. This is an issue that's very much of interest to those of us in the Global Spaceport Alliance. And in the report, which was released in December, GAO concluded that the FAA was really the right organization to understand the issues and assess the advantages and disadvantages of different potential approaches for supporting U.S. space transportation infrastructure. And it recommended that the FAA perform such an examination. Now, unfortunately, the report noted that the FAA has not yet conducted a comprehensive review of existing funding mechanisms or examined other potential alternatives, and it apparently has no plans to do so in the future. So it sounds like some further discussions may be warranted there, and I encourage all of you to mention to the FAA that we think that would be a helpful thing for them to do going forward. So all in all, a really busy time, a lot of challenges certainly with COVID and other things, but commercial space is really going to town, and I think the rest of this year is going to continue in that vein. So with that as an intro, why don't we start with our speakers. First up will be Will Cromartie, and he's got a bachelor's degree from New York University, an MBA from Johns Hopkins University, and he is currently serving as an account executive with Spire Global, with responsibility for establishing and expanding aerospace partnerships with federal agencies, managing multi-million-dollar deal pipelines, and closing record-setting deals for what has become the world's largest constellation of multi-purpose remote sensing satellites. So, Will, over to you.
All right, can everyone see the slides there? Perfect. So thanks for having me here. I'm Will Cromartie with Spire Global. So I'm going to spend about 15 minutes here, or between 10 and 15 here, speaking about spaceport weather. And this has been kind of a recent endeavor of ours that we've started looking into more and more. And so I'll start off with kind of a general background here of Spire and who we are, and then go into the specific weather considerations for spaceports and what we're looking at on those right now. So starting off at a very broad level here, we have 112 satellites currently in orbit. These are all 3U satellites, so roughly the size of a loaf of bread, and we're doing about 10 launches a year. We've got about 30 ground stations right now, and we keep iterating and putting essentially new hardware up each time. These are all software-defined radio-based satellites, so there's also kind of a software element here too. And essentially what we're doing is we're pulling down data from space for a few major topics. So these are ship tracking, aircraft tracking, high definition weather data, and then we also do custom payload builds. So, you know, when we do 10 launches a year or more, inevitably we encounter launch delays. And, you know, when you've been in the industry for a while, you start seeing that there are really a couple major trends for why launches get delayed or get scrapped, you know, entirely. And so really, the major reasons that you tend to see here, you see unauthorized vessels that stray into the launch zone. So, you know, inevitably there's someone in a motorboat that wants to see a launch and they go where they shouldn't go. You get aircraft flying overhead. And then primarily it's weather delays, you know, issues with weather systems. So wind, clouds, and lightning tend to be really the biggest causes there for launch delays and launch scrubs. And so this is something that we decided to really start looking into, not just out of self-interest, but we think there's actually, you know, a lot of potential here. For the weather concerns specifically, temperatures below 48 degrees, that starts to be kind of a red line there because you start worrying about ice buildup. High winds, which I'll speak more about momentarily, not only at the launch pad, but at upper levels too. Cloud layers, and then also just risk of lightning strike and the concerns that has for fueling. So one of the main ways that we do this is something called radio occultation. And so, you know, for those that aren't familiar with this, it's actually much simpler than it sounds. Essentially what we're doing is we're looking at how GPS or GNSS signals go through the atmosphere and how they bend. And so all we're doing is collecting these signals that are already going out there from GNSS satellite constellations. And so effectively what happens is when these hit the atmosphere, they bend in different ways. You can think of it like when light goes through a prism. And the factors that cause it to bend are typically atmospheric conditions. And so, you know, by looking at exactly how they bend, you can learn a whole lot about temperature and pressure and humidity, specifically at upper levels of the atmosphere, where typically you don't have as much data as you'd like. So, you know, we're doing this right now for NOAA, NASA, and the Air Force, and a number of different entities that have an interest in that upper level atmospheric data specifically. In terms of what that actually gives you, this is a hypothetical flight path here, you know, looking point A to point B here. And the important part I want to draw your attention to here is that horizontal bar on the bottom. That's basically a map that's been built out of the turbulence someone could expect to see along the way, you know, the conditions that you would get at each flight level for that hypothetical point A to point B path. So, you know, you'll see entities in the aviation sector that have an interest here for environmental reasons or fleet model, fleet management purposes, you know, just fuel efficiency. So this is one that's definitely been of interest, but also has applicability to spaceports. So typically, if we want to take a look at a location like a spaceport and their specific weather concerns, what we want to do is do what's called a point optimized forecast. And what that means is taking your numerical weather prediction model in a broader sense and then tailoring it down to a specific set of geocoordinates. You know, you look at this specific set of coordinates and you factor in nearby weather sensors so that you tailor it down and downscale it to that location. And the reason you'd want to do that is, you know, if you consider a regional forecast and how you might have smaller obstructions, whether that's, you know, mountain ranges or even physical buildings, you want to be able to make sure that you have absolutely precise wind data for that spaceport location and that some obstruction at a very localized sense isn't giving you incorrect data based on a broader regional model. So here's just an example of that. You know, you take your traditional grid. You know, we're doing this right now on a 12-kilometer grid or 8th degree resolution for numerical weather prediction capabilities, but then pulling in sensors that would be at the site of the spaceport itself. And we do this for over 10,000 locations right now. And ultimately, this gives you the ground element, but then of course you still want to be able to pair that with the upper level winds, which is what we do right now, going up to about 70 or 80,000 feet. So ultimately what you do is you give yourself sort of a collection of red lines that you would want alerts on essentially. And that's to make sure that you don't have a wind condition at 20,000 feet that wouldn't show up if you're only looking at ground-based data. So here's just a sample bar chart here, looking from February 23rd going out to March 2nd, essentially what those wind conditions might look like. And this allows you to start predicting launch windows, or even giving you advance notice of delays that you might want to have for a spaceport. If you are going to need to scrub a launch, you're going to want to know as far in advance as possible about any inclement weather that may be coming. So in this case, wind speed and wind direction. Likewise, you might have an interest in fog or visibility concerns, and then also ice. So taking a look at the chart on the bottom there, you could pretty quickly determine that February 24th is probably not the day to do the launch. So in both a launch planning sense and also a safety perspective, that's where data like that would start coming in for icing concerns. You might also have concerns for cloud cover and air temperature. And so essentially here, the same concept, looking at where you have kind of those large spikes and how that might affect your launch schedule. And then also thunderstorms. You can see that February 28th here would probably be a bad day from a thunder and lightning perspective to conduct a launch. And so, this is predicted out, 5 days in advance currently for this one. So the weather variables that we look at, we've got a list of 50 or more that we tend to look at when we want to take a look at a spaceport and the weather conditions there. We've generally bundled these into a few major categories that we look at. The basic set of variables that everyone looks at, but then also the ones that traditionally have an aviation interest, getting up to those upper flight level conditions at about 70,000 feet, pushing up to 80. Clear air turbulence, for example, would be a concern for any kind of launch. Upper air, and then thunderstorm. And we've traditionally found that these are the ones of greatest interest for launch concerns. So just as one visualization, if someone is using something like Esri ArcGIS, taking a look here at a specific region, collecting ADS-B and AIS data for broader situational awareness, then a weather layer would essentially be overlaid on something like that. So you can see right here, just in kind of a general dashboard sense, likewise using ArcGIS, the ability to overlay that weather data on top of an existing situational awareness model for AIS and ADS-B presence. So I'll conclude it there, and I believe we have Bill up next.
All right, thanks, Will. So our second speaker today is Bill Conway. He has a BS in meteorology from Metropolitan State University of Denver, an MS in meteorology from the University of Oklahoma. He also has experience working as a research associate for the National Center for Atmospheric Research in Boulder, as a weather forecaster for Aeromet at Kwajalein in the Marshall Islands, and as a research scientist for the National Severe Storms Lab in Norman, Oklahoma. Currently, he's the CEO of Weather Decision Support Systems International. Bill, over to you.
I appreciate that. Can you send me the link to share my screen?
You should have it now.
I got it. Okay. Can everybody see?
Looks good.
Looks good.
All right. So I appreciate the opportunity to discuss what we're doing in as far as state-of-the-art weather observations and forecasting. Will is coming from kind of the top down, and we are coming from the kind of the bottom up in the way that we're approaching the forecasting and observations. So what we have is we have a system that we call the Launch Weather Decision Support System. And in general, you see over here on the left-hand side, these are all local ground-based observation platforms that collect wind profiles, thermodynamic profiles, lightning data, and then also integrating the NOAA data and NCEP data, and then bringing everything into a local scale model, and then running that model. And then on the other side of that, coming out with decision support products for local launch requirements, general construction at spaceports, And we have products for not only the forecasters, but also for the actual range operators to help them make better decisions to increase launch window availability and spaceport safety. I'm going to talk briefly about a couple of the instruments. One of them is called a microwave thermodynamic profiler, or a radiometer. And the purpose of the radiometer is to collect data from the surface through about 10 kilometers of temperature, relative humidity, vapor density, liquid density, and then there's other products that you can derive that are integrated. And so the idea then is that what you're doing is you're collecting these data sets as if there was actually a radiosonde balloon release. It's not quite as accurate as a balloon, but it's continuous. So you get a continuous profile updated every 5 minutes from the radiometer of these variables in the vertical. And there's over 300 of these microwave profilers are currently operating worldwide. Another instrument is called the Acoustic Wind Profiler, or SODAR. And what the SODAR does is it sends out sound waves, and it measures the winds in the vertical in very high resolution, basically from about the surface to about 200 to 500 meters above ground level. And so the purpose of the SODAR is to fill in the gap between the surface station and what I'm going to show next, which is a radar wind profiler. And these are the basic radar wind profilers that we've used. The size of the profiler determines how high in the atmosphere you retrieve the winds. So for instance, the profilers up here are boundary layer profilers, and they are, say, 3 to 6 kilometers. Then you step up into a little bit bigger profiler like this one that gets more to 6 to 8 kilometers. There's also mobile versions of this. And then there's the really big profilers. This one down here gets about 18 kilometers above ground. And this is installed at NASA. So this is the big NASA profiler. So the idea here is that you're bringing together all these different data sets and integrating them all to have better forecasts and also do decision support products that are tailored for not only the forecasters but also the range operators. This is another plot of the radar wind profilers. So here over on the right, these are your boundary layer systems, and you can see that the height that they get to over here on the left axis. And so you see as your requirements to go higher in the atmosphere increase, so does the size of your wind profiler. So that you go all the way from boundary layer profilers all the way out here to the NASA scale profiler. So generally then, at a spaceport, depending on your height requirements to get the winds in the vertical and the resolution in the vertical that you want the winds, then that drives the size of a wind profiler that you would have at a spaceport. This is an example of this boundary layer profiler that we have at the Abu Dhabi International Airport. And the thing that I want to point out here, these are wind barbs. This is height, and this is time on the x-axis. And so basically what you're seeing is you're seeing these really strong low-level winds called a low-level jet. And this is one this is one case that we had, and here's another case. And the point here is that there's no other way that you would see these winds occurring without a wind profiler sitting there measuring them. And in this case, it's at the airport, and so you've got all the pilots that would be screaming and yelling because they're in all kinds of crazy turbulence, but the forecaster would not have an idea of the scale of the winds, the depth of the jet, or the time of the jet. And so with the wind profiler, you can measure direct profiles of the winds in the vertical and use that for all kinds of applications. One of the things that has been happening recently is that the cloud computing infrastructure has dramatically increased to the point where you can actually run numerical weather prediction models. And so one of the things that we've been doing is a partner company called TempoQuest actually partnered with NVIDIA to set up graphical processing units to be able to use the numerical weather prediction runs on. And so what that does is it significantly speeds up the ability to run a numerical weather forecast model, and also to significantly increase the resolution of the model over what you can get from the government currently. And so the model of choice that we're using is called the Weather Research and Forecast Model. And so you see over here on the left-hand side, the idea is that you take all your instrumentation available, you put it in the cloud, you run the WRF model on it, and then out the other side, then you have decision support products for the meteorologists and for the spaceport operators. And so you can rerun the model. Right now, we're running it about over a small domain, and running it out to 24 hours and rerunning it every hour. And so over a 1 kilometer grid. So the difference then between what you can get from the National Weather Service and this is, number one, it's customized to the spaceport location. Number two, it's much faster and the data come out much quicker than the National Weather Service models. And number three is that you're ingesting the local data sets from the spaceports. And so what we're doing is we're using the longer term forecasts with the National Weather Service models, but when you start getting into that T-minus 24-hour range, then we're going to the GPU processing of the WRF model. Another issue, of course, at spaceports is lightning. And so there are several methods to watch not only for lightning that's occurring, but also triggered lightning. And so here on the bottom left here, we have a field mill. And so the idea is you set up the field mills at the spaceports, and the field mill measures the background electrical fields of the atmosphere. And so when that field tends to get over a certain threshold, then that's when you have to start worrying about a first strike. So the purpose of the field mill is really to predict that first strike, or at least not predict it, but at least alert you to when you have a potential for a first strike. And so there's a lot of areas where there's a lot of construction going on at spaceports, and then there's also the launches. And so the field mill not only helps with the launches, but also for triggered lightning, but also in the day-to-day operations at the spaceport. And so then another way to look for triggered lightning also is with aircraft. And so we have an aircraft that is instrumented with field mills and other instrumentation to fly through the cloud layers at the spaceport to determine whether any of the cloud layers are actually electrified. Because that can be a big issue, of course, is where you have clouds that are above the freezing level, but they have super cold water and they have ice in them. And so then when you shoot a rocket through it, then that can be a trigger that forces a strike. And so you want to know all these variables about the clouds that are above the spaceport. And so another thing that we're doing is algorithms that take the FAA lightning launch commit criteria into consideration and build decision support products off of those. And the purpose being is that right now, the LLCC requirements are really restricted. And so if you can build algorithms on them that say, okay, we know that this cloud deck is, 4,000 feet thick, and we know that the bottom of it is at 10 degrees C and the top of it is at -10. And so then from these algorithms, you can determine whether it's safe to launch or not. And the aircraft really proves that out also. So using the aircraft, you can really determine whether clouds are electrified or not. And then finally over here on the right-hand side, we also use the lightning detection network, the US Lightning Detection Network. And here's an example of you have a range ring. And so any lightning occurring within this range ring at the point from the center point is automatically alerted upon. And then we also work with a company to provide meteorological support, basically 24/7 forecasters. And so there is these outlook planners that are given out to the spaceport that of interest, basically red, green, yellow, and then real-time data, lightning alerts, like we just said, and then there's also mobile apps. And so the idea being is that the forecasters actually have access to the local data from the spaceport, from that instrumentation, and that's also helping them determine what their forecasts are for the particular spaceport. And this can start at like T-4 days for an actual launch, and then ongoing 24/7 support for the general operations. And then out of all of this, all the integration and everything, then you have a whole set of decision support products that can be customized for each spaceport, depending on what their particular weather concerns are. And so these kinds of products are red, green, yellow for the launch operators, simple displays, all the way to much more complicated decision support products that are built out for the actual forecasters that are doing the 24/7 forecasting and the launch support. This is an example of the LWDSS that is at the Kennedy Space Center. And so here is this is a wind profiler and radiometer. And then they also have the really big profiler that I showed earlier. And so here's an example of what's called a sounding. And so this is what you would get from a balloon launch. And every time you launch a balloon, it takes quite a bit of time for that data for the balloon to go up into the atmosphere and then transmit the data and have any value. Whereas what we're doing with the profiling system is we're updating this every 5 minutes. So every 5 minutes, the forecaster has a new sounding. And also with knowing the profiles of the wind, of course, there's the questions of max Q and what are the winds aloft, like Will was talking about. And so there's a whole lot of different data sets that you can integrate and come out with really nice decision support for particular spaceport requirements. And this is our most recent installation that we just finished. And here you see we have a radiometer here. Then this is what we call a quarter scale profiler. This one gets up to about 6 to 8 kilometers in the air. This is the SODAR, which is filling in that gap between the surface and the first gate of the wind profiler. And then this is the hardware shelter that we have all the hardware in and communications and power. And then here's a surface station also. And so what we're doing then is we're bringing the data into the hardware that's in the trailer here, doing all the processing, and then serving the data and products and decision support products out to the customers. And that's everything I have. Here's a summary slide. And basically then the idea is to bring in all the weather observations, do all the algorithms, all the numerical weather prediction, and then come out the other side with solid decision supports products for the forecasters and for the range operators. And I appreciate your time.
Excellent. Thank you, Bill. Okay, we have plenty of time for questions and comments and some good discussion. First of all, let me encourage everyone to consider changing your drop-down menu at the top center of your screen, and instead of view who's talking, you can change it to active cameras, and then we'll get Will and Bill and I up in terms of our camera views, and we can have more of a little roundtable discussion.
George, this is Melchor Antuniano from the FAA Civil Aerospace Medical Institute. I have one question. What systems could be used to enable the prediction or early detection of severe clear air turbulence at different altitudes over the spaceport? Particularly, that becomes relevant for, obviously, space flights with spaceflight participants and crew.
Okay, interested in thoughts from both of you. Will, any comments you have.
Yeah, sure. I mean, I think that's actually where, I mean, the topic of clear air turbulence is one where we've definitely focused a lot of effort in a predictive sense using radio occultation. And really, I think that ultimately is, you know, when I was pulling up the bar charts there in a predictive sense, we do something similar looking in a future looking sense for conditions like that as well. Even like the horizontal chart that I pulled up there for the work that we did in the past for FedEx for the point A to point B, that was actually a future looking one. And so we would probably do something very similar looking at clear air turbulence above a spaceport location.
Okay, thanks. Bill, any thoughts?
Well, I mean, the way that we would work with it would be the high resolution numerical weather prediction model, and then using that as a forecast, short-term forecast to predict turbulence.
Okay, great. Okay, so let me invite questions from everyone on the line right now. You can click on the little bubble up in the upper right-hand corner of your screens for the chat, and then type those in, and I'd be happy to invite some responses from our presenters today. Let me start with one for Will. It seems to me like the GPS occultation analysis techniques are relatively new. Are you finding reasonable acceptance of what that type of technology can bring from the major players? You mentioned you're already working with NASA and other folks. Could tell us a little bit more about the acceptance of that approach, and if that's been an easy or a challenging task?
Yeah, sure. No, we've actually found a huge amount of acceptance. Actually, it's going very well. I think one reason for that is that the underlying technology is something that that NASA was already doing, and we've essentially just kind of built on that and scaled that up. So, you know, in a sense, it's already very closely aligned with their existing collection methods and their existing goals, and it's just kind of building more capacity for the ability to do what they already wanted as an input.
Excellent. Bill, you mentioned this a little bit, but can you compare and contrast the kinds of forecasts that you're talking about being able to do with what the local National Weather Service folks do as they give the weather forecast on TV and radio and so forth?
So sure. So what we found is that a lot of the areas, the spaceports, they don't actually have dedicated meteorological staff, and so they're kind of winging it a little bit for like you know, using the local NWS forecast or watching the Weather Channel or whatever it might be to get their weather information. And so the difference is that the National Weather Service forecasts are not specific to anybody's spaceport operations. I mean, they are here to forecast and protect the general public, but not do site-specific forecasting like we're talking about. And so we're talking about not only having 24/7 meteorological staff help at a spaceport location, but also running the numerical models and having the instrumentation on the ground that really bundles everything together with the forecasters to produce a very customized forecast for a spaceport location.
Okay. Will, any other thoughts on that question for you?
I think also there's just kind of like the sort of the three-dimensional weather aspect of, you know, for launches specifically, you know, you want to have not just this flat two-dimensional forecast of the weather at a certain altitude, but also, you know, thinking about tens of thousands of feet above that, right? Every single, you know, micro pocket of weather that you're going to hit along the way if you do a launch today. I think that's really where, you know, when Bill and I have spoken previously about, you know, collaborating in some joint projects, it's like you were saying initially, you know, he kind of provides that, you know, bottom up and we do top down, and you get a marriage of the data sets there, so that you can really hit every single possible layer along the way.
Excellent. Okay, so here's a topic that I don't know how open you're able to be. I'm sure it depends on the details. I'm not asking you to share any proprietary information and all, but can you put some boundaries or broad ranges of the costs of weather monitoring services for a particular spaceport? And does that usually end up being like an annual fee, or is it forecast by forecast, or how does the costing model work to enable you to stay in business and yet provide a valued service? Will, why don't you start?
Yeah, sure. I mean, I don't want to say it depends, but I probably have to say it depends. But I think you know, there are probably a couple different factors I'd look at, right? One is how large of a geographic zone, because we would scale that based on the size of the launch zone. Also, whether there's an interest in historical data. For example, if someone wants to look at a launch that went wrong, you know, we're storing all this data historically. And so, you know, you would obviously have a slightly different pricing model for a historical or retroactive study versus one where you're doing things in real time. So, yeah, I would say, you know, I don't want to just give you a non-answer here, right? But I would say it really depends on what specific variables someone would want to loop in and whether they purely have an interest in weather or they have a broader interest in AIS and ADSB and kind of the situational awareness element of protecting a certain zone.
Okay. Bill, what can you share in terms of cost or philosophy of whether this is affordable to most spaceports and all the rest?
Sure. So the way that we've been approaching it is a couple of ways. One of them is to phase in a system. So, for instance, something that is almost immediately available are the 24/7 forecasts, right? So where you can call a meteorologist and get their opinion on what the weather is doing. They're already giving you daily forecasts and planners and all of that. And so that's something that can come online immediately. And then another phase would be to start to bring in instrumentation. And we can do that on either an outright buy or actually a lease is a lot better for a lot of people, because then there's not a large capital outlay. There's just more of a monthly lease fee, if you will. And so the systems that we're delivering they can run anywhere from a couple of $100,000 to, the NASA profiler that I showed, the real big one, that's $10 million. And so there's a whole range of applications between the Maserati system and the maybe not so Maserati system. And each one of those stages and steps can provide significant benefit to the spaceports. So what I'm trying to say then, I guess, bottom line is that the first thing to do is evaluate what the requirements are at a particular spaceport, and then come in with the solution that can be staged through a few iterations to build it all out through either buying or leasing.
Excellent. Okay. We've heard a little bit about this during the presentations, but we had a question come in from the folks at Spaceport America. What comparisons do we have from balloon systems in terms of either history or corroborating or verifying the kinds of data that you're able to provide with the systems you're talking about here? Bill, would you like to start?
Sure. So I didn't show it, but we have several comparisons between balloons and the profiling systems. And the temperature profiling system, the radiometer, usually performs really close, and the winds from the profiling system compared to the balloon are usually even closer. Now, you have to keep in mind, though, that when you release a balloon, it's going downwind. And so there's going to be differences between what it's actually measuring as it's ascending compared to where you launch it. But yes, for the most part, the profiling system is pretty accurate compared to the balloons.
Okay, very good. Will, any thoughts from you?
Yeah, I would say, we've thought about the balloon topic in the past, and I think in terms of timeline, it might even make sense to think of us as kind of falling a step before the balloons, in the sense that it can almost be complementary, because there's a certain cost that's associated with putting up those balloons. And if you have, if you're able to get data in advance that shows that the certain launch date that you would plan for, there's no way it's going to work for icing reasons or wind reasons or anything else, then essentially, we've looked at saving people money by having them not even need to launch those balloons on specific dates, because they already know the launch can't work, if that makes sense. And so, we definitely, for a very localized forecast, would still want to rely on technology like BILS or those ground sensors or balloons. But I think there's kind of the question of how you integrate those, and then also how you deploy them in a cost-effective manner, and even if you should be deploying them on a certain day, if that makes sense.
Good, thanks. Okay, let me ask you to put on your thinking caps and look to the future a little bit. Can you see a benefit of collaboration, networking, having a much bigger set of locations? I think, Will, you mentioned that you have 10,000 locations right now that you track the winds and so forth. If we signed up all or most of the spaceports around the country, around the world, and they were part of a regular weather detection and assessing and prediction capability, is that something that would have some synergistic benefits that you can see? Or Will, why don't you start?
Yeah, I would say definitely. I mean, as it is, we already get a lot of ground level data from airports, and so those are already very valuable sources of data, and there's no reason that wouldn't be the same for spaceports. I'd say absolutely.
Mm-hmm. Bill, what's your take on that?
Yeah, I totally agree. I think that the more instrumentation, especially the profiling type instrumentation, the better initializations that you can give to the numerical weather prediction models, and in turn, the better that they are going to perform. And so that's one thing that in numerical weather prediction that is significantly lacking are profiling observations. And so the World Meteorological Organization has various areas across the globe where they release balloons twice a day at 0Z and 12Z. And then those profiles go into the initializations of the numerical weather prediction models. But that's all there is. And so the more profile points that you can get out there, the more profile data that you can get into the numerical model initializations, which will, it's already been shown in previous studies that they make a big difference in the numerical weather prediction forecasts.
Okay. Got a question from the team out at the Arizona spaceport relating to potential differences in what you'd need or want to have for a horizontal launch site, essentially ones with runways that are like airports, versus the vertical sites. They're just going straight up. I know it's pretty much up to the user and the vehicle folks and all, but in talking to the teams, I'd be interested in your takes on how to determine what kinds of systems would a particular spaceport want to have to be able to take advantage of the technology that's currently available. Bill, can we start with you?
Sure. So from the aspect of a horizontal launch, then the wind, for instance, if you're purely talking about a wind profiler, then the height that the wind profiler can get, and thus the size needed, does not have to be as big as if you're doing a vertical launch. So that's one aspect of it. And another aspect of it is that you want to be able to do, like Will showed earlier, more of a flight path trajectory on the horizontal launches rather than a point above the launch pad for vertical launches. And then there's also the question of, well, are you bringing the spacecraft back, to land, or are you going point to point, spaceport to spaceport? And so all of that comes into consideration of what instrumentation you would have at a spaceport doing horizontal launches.
Okay.
So it can be customized either way for vertical or horizontal.
Okay. What are your thoughts on that, Will?
Yeah, I mean, I agree with everything that Bill said there. I think one other interesting consideration also, and that this isn't specifically a weather consideration, but I think for horizontal launch sites, they tend to be a little more integrated kind of into the broader air traffic management world, in the sense that often they're co-located. And one thing that I've seen lately is kind of a convergence of entities between the UAS sector, the drone sector, and the space sector. And so, we spend a lot of time looking at weather conditions, not only for spaceport topics, but also for UAS test sites. And so I think you're probably going to see kind of a convergence there in more of a forward-looking sense as well.
Okay, and one final question for each of you. We've got quite a range of different spaceports that are part of the Global Spaceport Alliance. Some horizontal, some vertical, some very mature with a lot of launches, some just getting started, some working towards an eventual operational capability. Be interested in your thoughts if a particular spaceport were to say, hey, I've already got a meteorologist on staff. What are the potential advantages of having an additional service or a different service such as the ones that we're talking about here today? Will, would you like to start?
Yeah, sure. I would just say the primary advantage is really just more data to work with, and also in more of a forward-looking sense, being able to extend that timeline for that meteorologist on staff, right? Not to replace them in any sense, but to allow them to make the call much earlier before you start having major capital expenditures that are associated with gearing up for that launch.
Very good. And Bill?
I think for meteorologists on staff, then the idea is give them more data to help them better with their forecast, and also provide the profiles for them to do with their forecasting, and also the high resolution numerical weather prediction type decision support systems that they can't get, that are not currently available from the National Weather Service.
Excellent. Okay, well, Will Cromarty, Bill Conway, thank you very much. This was a fascinating view. I learned quite a bit listening to you. I hope the rest of the group did as well. Let me pass it back to James for some closing comments today.
Okay. Thank you very much, George, for orchestrating that great session. Thank you, Will. Thank you, Bill, for answering all the questions that came at you. This whole session is going to be recorded, as you probably are aware, and will be available on our website, www.globalspaceportalliance.com. So if you or any of your teams missed any of this, they'll be able to hear it. The next session is March 25th. We're going to be having a really fun discussion on point-to-point and what the status of all that is. 1 o'clock to 2 o'clock, March 25th. So with that, thank you all very much for your attendance. I'm looking forward to hearing from you and seeing you again in March. Thank you all. Bye-bye.
Thank you.
Thank you very much.
Thank you.